implemented in that device. And that is how you become engineers. There's no other way of becoming a good engineer. So that should be the approach of studying. You know how I got all these things? How did you think that I have related a simple block diagram to a satellite's control? That is the mantra. Getting the point? Because when we read, we never link anything with anything. Only thing we saw, only thing we keep in mind is, have we marked the formula? Okay. Have we applied the correct thing in the exam? And it's okay. Because marks are important at the end of the day. Because when you apply for jobs, first thing they see is your percentage, right? So it is very important. So we will be talking about the PID controller, why I chose this controller is, all of you are actually aware of this controller. So how does a PID controller work? Please focus. How does a PID controller work? P stands for proportional, I stands for integral, D derivative, right? PID controller actually works taking error into picture. That means, just recollect the video that we saw. It moves like this, right? Correct? So at every instantaneous point of time, there is an instantaneous error. Am I right or wrong? Correct? So this control algorithm works only on error and tries to make that error near to 0. That is the basic of a PID, okay? And controller tries to reduce error in every iteration. Simple mathematics can be implemented in digital domain. I'll tell you what is this digital domain later on, just in some time. Now, look at the PID. I'll just put the same graph again so that it's very easy for us to map. There are 3 different parameters in a PID controller. Everybody knows that? Correct? Yes or no? Yes. Yeah. Kp, Kd, Ki. The proportional gain, the differential gain, and the integral gain. Correct? Now see what happens. Why 3 parameters are required? The first one responds faster to changes at point. Means what? It has to go from 0 to here, right? Huh? So if you increase Kp, the system will respond faster. The steady state error reduces. These are basic, points, principles on which a PID works. So if you tune Kp, Ki, Kd, you will be able to achieve a good response. Ki is integral gain. If you increase Ki, this becomes 0. It reduces basically. And Kd improves stability, reduces overshoot, improves response time, can be set exactly to get critical damping. Critical damping is what? Anyone knows? When there is no overshoot. Okay? So if you keep in mind what these parameters are used for in achieving a real controlled output, you can always change the parameters to get it done. And then there are some tuning challenges. Okay? See, you cannot keep on. If I say Kp is higher, will lead to faster change in set point, right? But you cannot keep on increasing Kp. There is a limit to that. Why? It will lead to less stability. So this is called as tuning. Tuning Kp, Ki, Kd. Okay? So there is a PID algorithm and there is a tuning method to that, which is called as Ziegler-Nichols rule. Have you heard of that? Which you study? Actually you study in your curriculum. So using Ziegler-Nichols rules, please refer to your textbook or Google it. Okay? You will understand how to get these values. And that is the system, function here for the controller. And the plant comes here, okay? It is called as Ziegler-Nichols rule. So what you are taught in class is the same thing that I have put on the presentation. Only thing is, I have related that to the practice. So you get Kp, Ti, and Kd. Okay, just have a look. I may not be able to teach everything now. Okay. Now with this, if you have this design approach, okay, you will be able to design a stable PID controller. But you have to apply Ziegler-Nichols rule, which I am not explaining here. Okay. If you apply, then you get these values. This value, when you plug into a system, okay, this, 100% guarantee that your system will actually work. It will work. So what you studied till now, which you thought is never implementable anywhere after you graduate, I'm telling you there are hundreds of satellites which have done this. So you can also do it. We have also done it. Okay. So this was the basic mathematics which you read in your theory, which I'm telling is actually implementable and has been implemented. Okay. So what you're studying is not at all useless. With this basics, now till now what we did, we just saw the theory, right? We delved deep into the subject of attitude control, correct? Understood what mathematics are used, what kind of controllers are used. We focused on PID. We saw the method of analysis of the transient response and the steady state response, how you should work on that using the Ziegler-Nichols rule to get a stable response, correct? This is the mathematics behind lots of satellites for stabilizing this. The next part is controlling designing the attitude controller of a satellite. Now this is the practical implementation. I'll discuss here what are the components, okay? What are the real components that we know that are available in our laboratory itself, okay, can actually be used to design a control system of a satellite. We are not using thrusters, okay, as I told you, we use DC motor. I'll tell you how DC motors can be made to rotate with a known velocity to stabilize the satellite.